Hey everyone, today we're going to look at different forms of energy and also the conservation of energy when we're dealing with only conservative forces doing work. So I have the definition of energy here. This is just my definition. It's a measure of an object's ability to affect its surroundings. If you look at the textbook, they all say that it's an object's ability to do work, which is really interesting because a lot of textbooks define energy before defining work. So I'm just trying to come up with a definition here that doesn't use the word work. It's a measure of an object's ability to affect its surroundings or other objects. And we know energy is measured in Newton meters or joules, so that capital J for joules. And we've already talked about one type of energy. We've talked about kinetic energy. There's lots of other forms, nuclear, chemical, thermal. Unfortunately, those other types of energy, we don't get the opportunity to discuss them a lot in this class. But we do talk a lot about mechanical energy. Mechanical energy is the energy that an object has due to either its motion or its position. So we have talked about kinetic energy, the energy an object has due to its motion. Any moving object has kinetic energy. We can use Ke, or what you might see, some books or resources are going to prefer to just use one letter, so you don't think it's a product here. So you could see something like this, Ek for kinetic energy, and it's just 1/2 mv squared, where m is the mass of the object and v is the speed of the object. Okay, so we have a new one today that I'd like to look at, and that is gravitational potential energy, the energy an object has due to its position, but more specifically, due to its position in a gravitational field. So the higher up an object is, the more dangerous it might be, or the more it can affect its surroundings. So if you are higher in a gravitational field and you release that object, it has a greater ability to affect its surroundings. So gravitational potential energy, GPE, or what I'll use, because a lot of potential energy, we like to just use the capital U for potential energy and then G for gravitational. So gravitational potential energy is just mgh, where m is the mass of the object, G is the gravitational field strength, 10 meters per second squared on Earth, and then h is how high you are from the surface of the Earth. So the higher you are from the surface of the Earth, the more dangerous it would be to fall from there because you have a greater potential energy. Another type of potential energy that we have is elastic potential energy, the energy an object has due to its displacement from some equilibrium position. If you think about materials that are stretchy, like a bungee cord or even a spring, they have a natural length. If you just lay a spring down on a table, it has an equilibrium length that it would prefer to remain at. And if you stretch that object out, it starts to pull you back in the opposite direction. It's trying to return to its original length. And we call that displacement from equilibrium, and that energy that's trying to pull you back in, elastic potential energy. Same thing if you try to compress a spring. If you compress it and make it smaller, it wants to push you out. It wants to return back to its original length. So elastic potential, EPE, or better yet, US. So that's potential energy of a spring is 1/2 kx squared, where K is what we call the spring constant, which you can think of as the stiffness of the material. So a spring that is more stiff is more difficult to change its length. So if you press really hard and you change it from its equilibrium length, then it's going to press out a lot more firmly. So that spring constant we want to think about as the stiffness of the material. And then X is how far has it been displaced from its original length. So how far have you stretched that bungee cord? How far have you stretched that spring from its original length? So if you don't stretch it at all, then there is no spring energy. That's just the displacement there, not the total length of the spring. Okay? Energy is a conserved quantity. That means that even for the entire universe, energy cannot be created or destroyed. It can just be transformed from one form to another. And in the absence of non-conservative forces, all the mechanical energy of an object should be conserved. That means it remains constant. So again, total mechanical energy is just the sum of the kinetic energy and all of the potential energies. So whether that be spring or gravitational, or even in some cases both. Conservative forces are any forces that are related to a potential energy. So, for example, the force of gravity, the spring force, any elastic force that you have is related to a potential energy. So that's a conservative force. And as long as all the forces on your free body diagram are conservative, then the mechanical energy of an object is going to remain the same. Non-conservative forces would be something like a normal force when you collide with something, or maybe a thrust from an engine where energy could be added to the system or taken away. There can be non-conservative forces that don't change the mechanical energy, and that is if they're not doing any work. So in lots of cases where maybe the normal force is perpendicular to the velocity, we know it's not doing any work, so we don't have to worry about it changing our mechanical energy. Okay? So we can use this idea of conservation of energy to help us solve more and more challenging motion problems. So I have one here that's just a ball being dropped from 10 meters high. And I want to know the speed of the ball just before it hits the ground. Now, that's not that difficult. That's something that you could do with kinematics. And the reason you could do it with kinematics is when this object is dropped from 10 meters above the ground, you know that it's moving in one dimension, and also that it's a constant acceleration. So this really is something we could do with kinematics. I just want to show that we can also use energy to solve this problem, and then we'll look at a more complicated one where kinematics really isn't a good suitor for that type of problem. Okay, so let's take a look at this one. The ball is dropped from 10 meters high. If I were to draw the free body diagram, I have only the force of gravity, which is a conservative force, so I don't have to worry about my mechanical energy changing at all. So that means if I call this first one position A, and then just before it strikes the ground, if I call that position B, this means the total mechanical energy at A has to equal the total mechanical energy at B. And we know mechanical energy is just the sum of the kinetic energy at position A plus the gravitational potential energy at position A plus the spring energy, but there's no spring or elastic material here, so I'm just going to deal with those two, kinetic and gravitational potential energy, and that should equal the sum of the kinetic and potential energy at position B. Now, at the beginning, this object is dropped, so we can say the initial velocity is 0, so it starts with no kinetic energy, and we can also say that just before it strikes the ground, the height is 0. So there's no gravitational potential energy at the end. So basically what we're seeing here is all of the gravitational potential energy that you start with is being converted to kinetic energy due to the force of gravity. So the force of gravity is doing work on this object, converting gravitational potential energy into kinetic energy. And the gravitational potential energy that I start with at position A, due to the height at A, is just mgh, and that should equal the kinetic energy at position B, due to the speed at position B. So I have mgh is equal to 1/2 mv squared. Since there is a mass on both sides of the equation, I'll go ahead and cancel that mass out. And then I'm trying to get v by itself. So I'll multiply by 2 to take care of the 1/2. So 2 times g times the height at A is equal to vb squared. Of course, I don't want vb squared. I just want vb. So I'm going to take the square root of both sides. And I get that the velocity at position B is just equal to the square root of 2gh. And that result should look familiar because that's exactly what you would get if you did the third kinematic equation where h is the displacement. And it turns out that the third kinematic equation comes from the conservation of energy. So we can now get a numerical value for that velocity at B. So we have square root of 2 times 10 times the height, which is also 10, and that is the square root of 200. So we'll put that in a calculator real quick, and I'm getting about 14.14 meter per second for the speed just before hitting the ground. That's the exact same result that you would get from kinematics. But if we take a look at a more challenging example where kinematics really isn't going to be a good choice, something where, like a roller coaster, the direction of the velocity is changing as the angle of the incline keeps changing. Also, if I think about the free body diagram, I've got a normal force and a force of gravity. And if I keep drawing the free body diagram at different positions, you'll notice that the direction of the normal force keeps changing based on the incline. And force of gravity is always down, and it's a conservative force, so I'm not really worried about it. The normal force is a non-conservative force, But in all cases, and I'll do this in a different color, in every case, the velocity is tangent to the ramp, along the ramp. And we know that the normal force is perpendicular to the ramp, so it's not doing any work. So that's good for us. As long as the normal force is not doing any work, then we have just a conservative force that's doing work, which means the mechanical energy has to be conserved. So even though this is something that I could not do with kinematics because the acceleration keeps changing as the direction of motion keeps changing, I can use energy, since energy in this case is conserved. So I can say that the total mechanical energy at position A has to equal the total mechanical energy at position B. And at position B, our roller coaster cart is released from rest. So I'm tracking the mechanical energy, which is the kinetic plus the gravitational potential energy. And that should equal the total mechanical energy at position B as well. So we can look at the kinetic energy at B and the gravitational energy at B. Now, if this object is released from rest, I can say that the initial kinetic energy is 0. The initial potential energy is just mg times the height at A. At position B, we can say the kinetic energy is 1/2 times VB squared plus the potential energy. And again, this time it's not necessarily 0 because we are not at the ground. So I'm going to say this is mg times the height at B. And I'm running out of room there, so I'm going to move down to the bottom. So we have mg, height at A, is equal to 1/2 mvb squared plus mghb. Now, all of these heights, you'll notice, were measured from the ground. That's what I would call my reference level. So the thing about gravitational potential energy is that it's not an absolute. It is based on some reference level. We need some area to compare to. For example, right now I'm on the 3rd floor of my building, and I might call the floor my reference level. So anything sitting on the floor, I would say has 0 gravitational potential energy. But if I went up and I asked somebody on the 4th floor how much gravitational potential energy these things have, they're going to say that they have a negative value because all of these objects are below their floor. And if I go down to the 1st floor and I ask somebody, they're going to say that all the objects in my room have positive gravitational potential energy because they're above their heads. So that's a problem. If we don't have a universal reference, then we're saying different things. We're getting different values, and that's no good. So as long as we are explicitly stating our reference level and we're all measuring from that same reference level, then we're all going to get the exact same values. And what's most important when we look at gravitational potential energy is really the difference between these two positions, A and B. So I know that from A to B, this object has dropped by 45 meters. That's what's important. No matter what frame of reference we use, that object has gone down 45 meters in the gravitational field. So I've chosen the floor to be my reference level. If you were clever, you may want to use the top of position B to be your reference level so that at position B, there's no gravitational potential energy. But either way, since what's important is the change of 45 meters, we're still going to come out with the same results. Okay? So again, I'm using the actual ground as my reference level, and I want to go ahead and see if I can simplify this to get the velocity at B. Now I am noticing a mass in every single term. Make sure it's in every single term before you cancel them out, but now I can just divide everything by mass, and it's gone. I need to move GHB to the other side. So G times the height at A minus G times the height at B is equal to 1/2 V squared. And then to get V by itself, I'm going to multiply by 2, and I'm going to take the square root again. So I have 2 times GH at A minus GH at B, and then take the square root to get V. So that is the square root of 2 times 10 times 140 minus 10 times 95, and I'm coming up with 30 meters per second for the speed at the bottom, 30 meters per second. Now, if you were clever and you chose your reference level to be right here at the top of position B, then you would have had only gravitational potential energy here at A and only kinetic energy here at B. So you could have said the following. The height at A is just 45 meters. So mass times 10 times 45. And then you have only kinetic energy at position B if your reference level is the height at position B. So that's 1/2 mvb squared. Again, you're noticing here that the mass cancels out, which is really useful because I don't know the mass of the roller coaster cart, but the mass here doesn't matter. So I can't actually get a numerical value for the potential energy or the kinetic energy without knowing the mass, but I am able to solve for the velocity. So here we have 2 times 10 times 45, and then take the square root. And using the position B as my reference level, let's see, 2 times 10 times 45. I'm also coming up with 30 meters per second for the velocity. So just make sure that anytime we're doing mechanical energy and gravitational potential energy, that you choose a reference level, you make it explicit, you say exactly how you're using your reference level, and then you're able to calculate values like velocity. That is something that we could not have done with kinematics. It would have been impossible to do because of the changing acceleration. So energy is going to unlock a lot of 2- and 3-dimensional motion that just wouldn't be able to be solved using kinematics alone. Okay, so that is it for our extra types of energy and working on conservation of energy with conservative forces doing work. Thanks for watching.